Hi folks, today we're going to learn about function notation, and some students find function notation confusing. It is a new way of of writing basically the y variable in an equation. It may seem confusing at first, but it is actually a really handy notation system because it simplifies communications about equations. You can have multiple equations and you can label them F, G, H, I, and differentiate between them without having to write out the whole equation. So you can say, look at equation F, look at equation G, and use the terminology in that way. What we're going to find is, and I just have this quick example here, when does f of x equal 1? What we're going to find is that f of x is just kind of a new way of writing the variable y. So I'm basically asking here, when does y equal 1? Well, y equals 1, let's see, here's y equals 1, and that equals 1 here at this point when x equals 3, and here at this point when x equals negative 3. So there are two places in this function where f of x equals 1. That's at x equals negative 3 and at x equals 3. Now, this one is a little different to interpret. F of 0. What is f of 0? Well, this notation is telling me, hey, when x equals 0, notice I replaced the x with a 0. When x equals 0, what does y equal? So I'm still asking, what does y, f of 0 still is replacing the y variable. But I'm asking, when x equals 0, what does y equal? And here's my answer down here. When x is 0, y is this negative 2 value. So when f of 0 then, in fact, equals negative 2. Because this function, this graph, when x is 0, has a value of negative 2. So let's look up kind of the formal definition. Function notation uses f of x, and that's how we pronounce this symbol, f of x, to represent y in an equation. So instead of writing something like y equals negative 4x plus 7, we're going to write f of x equals negative 4x plus 7. This is not a multiplication problem. This is notation that says the function of a variable x. So let's see how to interpret this. Use function notation to evaluate and interpret. Evaluate f of x when negative 4x plus 7, and evaluate it when x equals 2 and when x equals negative 2. So here's my function. I've written it twice because I need to evaluate it twice, once when x equals 2 and once when x equals negative 2. And that's what I'm going to do in the equation. I'm going to go ahead and do 2 first. And all I'm doing here is, if I have f of x, I'm making this f of 2. And that's telling me to go ahead and replace 2 wherever I see an x value. So I'm going to have negative 4, and it's not going to be times x now, it's going to be times 2, plus 7. And so if I simplify what I have here now in the equation, negative 4 times 2 is negative 8, plus 7, so altogether that equals negative 1. So f of 2 equals negative 1. Let's look at this example over here. Negative 2 is my x value, so I'm going to replace it wherever I see x. F of negative 2 equals negative 4 times negative 2. Again, I'm just taking that x and replacing it with a negative 2, plus 7. When I have negative 4 times negative 2, that is positive 8. And positive 8 plus the 7 gives me 15. So f of negative 2 equals 15. So I have now evaluated this, this function for two different values of x, when x equals 2 and x equals -2. Let's look at another function and evaluate it for various values of x. G of x, this is a different function, so I went ahead and gave it a different letter. G of x equals -1 minus 1. And I've just written that equation 3 times here because I'm going to use 3 different values for x. All right, when x equals -4, I'm going to replace all my x's that I see in this equation with -4. So g of -4 equals -4 minus 1. So notice, there's a negative sign here in front of the x. I have to keep that negative sign there because it's part of the equation. But then I have to replace my x value with -4. So it's important to have both of those negative signs there because when you have a double negative, -1 times -4, it's actually going to give me a positive value. So -1 times -4 is 4. Subtract 1, and when I evaluate this expression, I get the final answer of 3. G of x when x is -4 equals 3. Remember, at any time you can pause the video, try to work a problem ahead of me, and then resume the video and see if you've got the right answer. G of x, I've checked -4, let's check 0 now. I'm going to plug 0 in wherever I see x. And here, -0, you can't have -0. 0 is just 0, so the negative sign is going to disappear. But I'm going to subtract 1, and that's going to give me g of 0 equals -1. So once again, I've evaluated g of x for the value x equals 0. And lastly, I'm going to plug in 1/2 where I see x. So g of 1/2 equals -1/2 minus 1. -1/2 minus 1 is going to give us -1.5 or -3/2. So g of 1/2 is -3/2. So that's kind of the basics for how to interpret function notation. You can plug different values in for x, or some occasions you want to leave x as a variable there. So let's look at kind of a real-world scenario and what kind of function we might have here. Let f of t be the outside temperature in degrees Fahrenheit, t hours after 6 a.m., explaining the meaning of each statement. Okay, so here I don't even have an equation. I can't plug any values into an equation. I'm just told that this function equals 58. This is another benefit of function notation. We don't actually have to know the equation. We can just be looking at a graph or looking at the result of the equation, of the calculation. Now, f of 0, remember, means the outside temperature. The outside temperature when we are t, remember this 0 is where the t should be. So we must be t hours after 6 a.m. We must be 0 hours after 6 a.m. Now, 0 after 6 a.m. is just 6 a.m. It's still 6 a.m. So what I'm finding is that the outside temperature at, I'm going to just replace this with 6 a.m. is 58 degrees Fahrenheit, because that outside temperature at 6 a.m. is equal to this number here. And I'm told that this function gives me the outside temperature in degrees Fahrenheit. Let's look at the next example. F of 6 equals n. Okay, well, what does f of 6 mean? Remember, f of t means the outside temperature. So again, this is about the outside temperature. T hours after 6 a.m. This time I'm 6 hours. 6 is here in the position where T should be. So I know I'm 6 hours after 6 a.m. 6 hours after 6 a.m. That brings me up to 12 o'clock, 12 noon. So what I'm really saying is the outside temperature at noon is, it's N. N isn't a temperature or a numeric temperature, but it does represent a temperature. So my answer would be N degrees Fahrenheit. So I'm not writing this statement. 6 hours after 6 a.m. is just noon, so I've got that there. But I do know that my temperature at that time will be N degrees Fahrenheit. And if I had more information, I could perhaps calculate or derive N. Let's look at one more example from this same scenario. Here, I have the function with regards to this particular variable, but it doesn't equal anything. I say that it's less than another version of the function. Okay? So f of 3.5, that's the outside temperature, 3.5 hours after 6 a.m. 3.5 hours after 6 a.m. Now, I don't really want to write that. I want to write down a number time. 3.5 hours after 6 a.m. is 9:30. So I don't have to write it this way. I can just write at 9:30. Now, in the previous examples, I had a number I could plug in this position. There's no number I can plug in for this example, but I can say that this outside temperature is less than some other temperature, and that other temperature is the outside temperature. This is another version of the function f. The outside temperature when we're 9 hours after 6 a.m. And what that means is 9 hours after 6 a.m., let's say 3 hours takes us to noon, and then, 6 hours takes us to noon, and then another 3 hours takes us to 3 p.m. So I don't have to say 9 hours after 6 a.m. I can just say 3 p.m. And my statement is finished. The outside temperature at 9:30 is less than the outside temperature at 3 p.m. What else can we use function notation for? Up to this point, I've told you what x equals or what t equals when I say f of x or f of t. In the next example, I'm not told what x is, but I'm told what the variable means. I'm told what h of x means. So here's my equation, h of x, the function h with x as the variable, equals 2/3 x minus 5y. I'm not told what x equals here, but I am told what h of x equals. It equals -7. So I'm going to plug -7 here where my h of x is, and then that equals 2/3 x minus 5. I now have a solvable equation. I have an equation with just one variable, and so I can calculate to solve for x. So how do I get x all by itself on one side of the equation? I need to get rid of the 5 and the 2/3. I'm going to get rid of the 5 first, because when you solve for a variable, you go in reverse PEMDAS order. You want to get rid of any addition, subtraction things first. So we're going to add 5 to both sides of the equation. After adding 5 to both sides, this -5 and +5 cancel out, and I'm left with -2 on this side of the equation. And on this side of the equation, I have 2/3 of x. The next step for getting x all by itself is to get rid of the 2/3. The 2/3 is multiplying the x, so I want to divide both sides of the equation by 2/3. Of course, when you divide by 2/3, when you divide both sides of the equation by 2/3, what you're actually doing is multiplying by the reciprocal. When you divide by a fraction, you end up multiplying by the reciprocal. So when I say that I'm dividing by 2/3, what I'm actually doing is I'm multiplying by 3/2. When I divide by 2/3, I'm dividing by 3/2. When I multiply by 3/2, I've got 3 up top in my fraction and 3 down below, so those cancel out. I have 2 up top in my fraction and 2 down below, so those 2's cancel out. I'm left with x on the right side of the equation. And on the left side of the equation, my 2 and my 2 cancel out, although that's actually still a -1 left behind. The negative is left behind. And -1 times 3 is -3. So in this example, and I should have used a dot as my multiplication sign, not an x, I apologize, is x equals -3. Let's look at another example. How do we just go ahead and create a graph with this function notation? Graph f of x equals 2x plus 5. Well, remember, f of x is just a different way to write y. So I can still create a data table of x values and y values, except this time I don't have to call them y values, I can call them f of x values. And so I can still create a data table and then plot a graph accordingly. So if I'm going to choose some values here, this isn't a story problem. I don't have any particular reason to just pick positive numbers, so I'm going to go ahead and pick positive and negative numbers. I'll start with -2, -1, 0, 1, and 2. Now, remember, when I choose my x value, I can plug it back into the equation and then evaluate the function for that value of x. So what I would want to do here when x equals -2, I would want to go back and plug in -2 wherever I see an x value. So that would be 2 times -2 plus 5. When I do that, 2 times -2 is -4, plus 5 is 1. So 1 is my y value, or my f of x value, for this particular data point. Let's do x equals -1. If I plug -1 in to my equation, I have 2 times -1 plus 5. Now, 2 times -1 is -2, plus 5 is 3. So now I have a value of f of x for when x is -1. Plugging in 0. 2 times 0 is 0, plus 5 is 5. Plugging in the number 1. 2 times 1 is 2, plus 5 is 7. And then plugging in the value 2. 2 times 2 is 4, plus the 5 is 9. So I now have all my data points. I know my x values. I know my y values, or f of x values. And now I need to plan my graph accordingly. I have a variety of x values. I've got some positives, some negatives. So I'm going to go ahead and split this down the middle. So I've got some positive values of x to put on the right side and some negative values of x to put on the left side. For the f of x values, I have all positive numbers. So I'm going to keep my axis, I don't know, fairly low down here, like this. And I have plenty of room in the y direction for each tick mark to be worth 1. So that if this is 2, this is 4, this one's 6, this one's 8, and this one's 10. And that way I have room to go up to 9. Notice each mark is worth 1 unit of f of x, or you can label this y if you're still more comfortable with doing the y. But I only labeled every other number just for simplicity so the graph didn't get so crowded. Let's label our x-axis now. I have room to go, out, I can have 2 marks be worth 1. So I can label this 1, 2. This is 0. This is -1, and this is -2. And if I plot my data points, when x is -2, y is 1. When x is -1, y is 3. I'm halfway between 2 and 4 here. When x is 0, y is 5. When x is 1, y is 7. And when x is 2, y is 9. If you don't have a story problem and you're not given information to make you think that the data are discrete, a general assumption is that the data are continuous. So I'm going to go ahead and do my best job at trying to draw a straight line here. Not perfect with my tablet, I know, but draw a straight line between the points because this is a continuous function. You don't just have to have whole numbers like 0 and 1 and 2. You can have half numbers like a half or 1 and a quarter. So this is the strategy for taking an equation and plotting it on a graph. You can make a data table and get your values of x and y in that way. Let's do one more example. I'm sorry, 2 more examples. Modeling real life. So this graph shows function g, and it shows how far off a helicopter is from its destination, x hours after taking off. The helicopter does a second flight, and it's represented by this function here. Which flight takes less time? There are a couple of different ways to approach this problem. One way is to go ahead and make a data table for graph 2. So we're going to make a data table for graph 2. And then we can figure out then how many hours the helicopter is from its destination by figuring out what the x-intercept is. So let's go ahead and make this data table with our x values and then our f of x values. And I want to do at least a few data points here. Let's do 0, 1, 2, and 3. So when x is 0 and I plug 0 into this equation, I'm going to do 350 minus 0 because 0 times 125 is just 0. So when I do that subtraction problem, I'm going to get just 350. So there's going to be a data point at 0 and 350 right here. How about when x equals 1? Well, when x equals 1, then I do the equation 350 minus 125 times 1. So that's 350 minus 125. And when I do that calculation, I get 225 as my answer. So when x equals 1, y is 225 right here. When x equals 2, I plug 2 into the equation wherever I see x, and I'm going to do 350 minus 125 times 2, and that's going to give me the answer 100. So when x equals 2, y equals 100. And lastly, for x equals 3, I am going to do 350 minus 125 times 3. So I'm going to do 350. I'm going to end up minus 375, and I'm going to get negative 25. I didn't graph my last data point here. When x is 3, y is negative 0.25. So what I have here is a straight line. If I can kind of connect all my dots here, which again I'll try to do very carefully. If I connect all my dots, if I draw a straight line through my data points, then I have a slope, a downward negative slope, but it's a bit steeper than the original graph was. And I can see that the graph crosses the x-axis just a little bit sooner in a little bit less time than the original graph did. So I did a data table, and then I made a graph. I graphed the second equation. And then when I did that, I'm able to find the x-intercept. Find x-intercept. In this example, I don't know, if that's 2 and that's 3, I'm more than halfway between the 2 and 3. I'm going to call that 2.75. 2.75 hours as my approximation of what the x-intercept is from this graph. There is another way to answer this question. It again involves finding the x-intercept, but not using a graph, using algebra instead. So method number 2, we're going to set f of x equal to 0. And once we say y is 0 or f of x equals 0, that's going to help us to find the x-intercept. So let me set the function equal to 0. Instead of writing f of x equals 350 minus 125x, I'm going to say 0 equals 350 minus 125x. This equation only has one variable, and my goal is to solve for that one variable, x. So how do I get x by itself? The first step is to do reverse PEMDAS, to add or subtract any values that I kind of see attached to x. So I'm going to subtract 350 from both sides of the equation, and I'm going to get negative 350 equals negative 125x. Again, my goal is to get x all by itself. So I'm going to divide both sides by negative 125, negative 125. And when I do that, these numbers on x cancel out. So I'm left with just x on the right-hand side. And negative 350 divided by negative 125 is 2.8 hours. Okay. Now, if we compare this method 2 to the answer we got with method 1, there is a difference. I got 2.8 the second time, but 2.75 the first time. That is why method 2 is actually the better method for solving questions having to do with equations, as opposed to doing graphs. It's better to use algebra than use graphs, just because your ability to read the graph depends on how carefully you drew the graph, how straight your line is, and you don't have any of those problems if you set f of x equal to 0 or you solve the problem algebraically. There's one more type of problem we need to look at, and that is evaluating functions that have two variables in them. Again, this has its own special kind of notation. F of x and y. So I'm not just saying f of x anymore, I've got x and y in parentheses. And that means I'm inputting two variables. I'm inputting an x variable and I'm inputting a y variable to see what I get. So if I want to input an x and a y, as shown here in this expression, to evaluate this expression for 3 and 4, the variables are given in the same order that they are listed in the function. So 3 is going to represent x and 4 is going to represent y. So I'm going to plug in a 3 every time I see an x, and I'm going to plug in a 4 every time I see a y. I see another x here, so I've got to plug a 3 in for that. So what I need to do here is 2 times 3 times 4, and that's going to be 24. 2 times 3 times 4 is 24. And then I'm going to subtract 3. 24 minus 3 is 21. So I have just determined that the function where 3 is x and 4 is y equals 21. Sometimes functions with two variables are expressed using something that looks like function notation, but sometimes it's written in a totally new notation with totally new defined symbols. So here's an example where a triangle means some sort of relationship between x and y. And then we're told what that relationship is, x times y plus 5/8. And then here I'm given two numbers to plug into that original combination function. I know that these numbers need to be plugged in because the symbol is the same in the original notation as well with my given variables. Once again, the order, if x is listed first and then y, then you get the same thing with your variables. X is going to be 5 and 2 is going to be y. So if I plug in my values where they belong, 5 times 2 plus 8, well, 5 times 2 is 10, plus 8 gives me a total of 18. So I've just determined that my function x triangle y equals 18 is the solution to this particular problem. I hope this helps.